Okay, welcome back. Monday. Exciting. Today, we're going to start up Chapter 5, phase modulation and frequency modulation, what I referred to last time as angle modulation or exponential modulation, or what the book calls nonlinear modulation. First, a public service announcement. I want to give you fair warning. I believe that our second exam will be Monday, April 14th. I will officially announce that Wednesday or Monday, but I want to just give you a heads up that this is the date that I'm thinking of. What I like to do is I like to give you 2 weeks after we finish a particular subject, and that means that when I get through section 5.1, which I pretty much should get through today. I might spill over a little bit on Wednesday. Then 2 weeks from that time, we'll have the next test. And so it's looking like it'll be April 14th. It's looking with high probability that it'll be Monday, April 14th. And the subject, and they will cover chapters 4, which is AM, and the first section of chapter 5, chapter 5.1. And then I will also tell you that there will be 3 problems. One of the problems will come from the homework of chapter 4. Okay? I'll give you Appendix E. But other than that, it'll be closed notes, closed books, no calculator. Okay? And I'll make an announcement to that effect. I'll make an announcement to that effect on e-learning. Okay? So today we'll talk about FM and phase modulation and angle modulation in general. And as I talked about last time, we have been looking at cosine omega t forever. And that's one of our favorite functions. Not just in this course, but in nearly every electrical engineering course that you've taken. And you're so used to seeing the argument omega t that you forget a little bit about it. You forget where it comes from. Just take a look at the units of omega t. Omega has units of what? Radians per second. And what are the units of t? So the units of this are radians. Radians measures what? An angle. An angle of a circle, of a particular section of a circle. And so really what we're always going to be writing is cosine of some angle, theta. Cosine of some angle theta. Okay? Now, if I compare this and this, if I compare those 2 equations, then what this goes to is cosine of theta, which is a function of time. Okay? And so what this is telling me, what this formula is telling me, is that I'm asked to take a cosine that is of an angle, and the angle is progressing in radians as a function of time. And so what I have, if I'm just looking at this, we tend to think of a static triangle. The cosine is the adjacent over the hypotenuse. So it would be the ratio of this length to this length, taken again and again and again. Okay? Now, if theta is a function of t, then this angle of the triangle is changing. So at first it's here, then it might be here, then it might be here. In fact, if it's cosine of omega t, then we say that the angle this angle is increasing linearly with time. If I wait twice the length of time, my angle is twice the size. I've accumulated twice the amount of phase angle. But there's no real reason why I have to stop with a linear increase in those radians. Or in fact, there's no reason why I have to go monotonically increasing the radians. I can increase, I can hold for a while, I can increase some more, I can even, well, it's hard to imagine reducing the total number of accumulated radians. But in fact, you can do that if you're willing to accept negative signs in there. So really, what we want to do is we want to be much more general about how we think about these cosines. And so, for example, if I talk about frequency modulation, if I talk about the term frequency modulation, then what those words suggest is that the frequency is now modulated, or the frequency is now changing with respect to time. The frequency is now changing with respect to time. Okay? Now, so what I'd like to do is I'd like to focus in on this particular expression. And I want to alert you to the fact that what we're going to be looking at we're going to look at these sinusoids, where the argument of the sinusoids has some very complex trajectory. The phase angle that accumulates in a very funny manner, or a very interesting manner, or a very non-obvious manner. Okay? And so what we're going to do is we'll start the clock at some t equals 0, and we will ask the question, how do I accumulate radians? If I accumulate them linearly, then I have an expression that looks like that. I can also accumulate them quadratically. I can also accumulate them with some sort of sinusoidal dependence. But what you should be starting to look at, from now on, whenever you look at a cosine, you should look at the argument, and you should say that argument can be very complicated. The way I accumulate phase, the way I describe the accumulation of phase, can be complicated, interesting, and very, very useful. Okay? Now, let's just take a quick look here. We're going to be looking at waveforms that are of this form. Theta of t is an interesting function. It is a function, so I can expand theta of t in a Taylor series. Not a Fourier series, but a Taylor series. And the Taylor series will have a DC term, or a constant term, a term that doesn't change with time, a constant phase term. Plus it'll have a term that's linear in time, and I'll label that omega ct, omega t, but I'll be definite about perhaps the carrier with the subscript. And then it'll have a higher order term, t squared, and I'll label that beta. And then, in general, it can go to infinity. So any function whatsoever can be shoved into the argument of the cosine to describe how you accumulate phase. Okay? This term here, I can further break down to beta t times t. And if I look at this, then I say, okay, my frequency of this term here is linearly increasing with time. My phase is quadratically increasing with time. My frequency is linearly increasing with time. Quadratic increase in phase with time. Linear increase in frequency with time. When I say phase, I mean the phase angle of the signal, the number of radians that I accumulate. This particular term is called a chirp. And I say that just to let you know that it is a very important signal. A frequency might, the tone might, I can't do it very well, the tone might start out at a particular frequency, and then increase in frequency. A linearly increased in frequency. like the chirp of a train coming at you that's been Doppler shifted. You know, as it rushes by you. So if I plotted this frequency, it could start out slowly and then get very, 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 very quickly, and the rate of change of this would be linear. Okay, and you can see how that's a very useful and very interesting signal in itself, the cosine of beta t squared. It's very interesting. It's very useful, for example, in radar, where you want a pulsed waveform that gives you both position and detection, position and speed of the signal that you're trying to, or the object that you're trying to track. Okay, so the chirp is useful. Now, the question is, if I have theta of t, what does that mean with respect to a frequency? Well, if I truncate my Taylor series there, then I just have one frequency, and it's a constant frequency. If I truncate it there, then I have a constant frequency on which I add a frequency that's linearly changing. And so I say, well, my frequency is omega c plus beta t. Omega c plus beta t would be my frequency, and notice that frequency becomes frequency dependent. Okay, so frequency goes to frequency as a function of time. So at any given instant, I have a unique frequency associated with this term. And one way to figure that out is to expand theta of t in the Taylor series and just divide every term by t. But that's really cumbersome. So what's another rule? What's another rule for finding the instantaneous frequency? Given our two examples. Okay, given our two examples. That one gives you a frequency of omega c. That one would give you a frequency of omega c plus beta t. What's another way of getting those two answers? I'm dividing by t, but what's another thing I'm doing? I'm differentiating. So if I differentiate theta of t, I lose that one. I get omega c for the first term. I get beta t for the second term. I'll get gamma t squared for the third term, probably over 2.
2 beta t?
2 beta t, and so on and so forth. So one of the things that I need you to remember, I need you to do, actually, more than remember, I need you to do every time you see this guy here, I want you to think about calculating the instantaneous frequency as the rate of change of the phase. The instantaneous frequency is the rate of change of the phase. However complicated theta of t is, there will be one frequency of my signal for every single attosecond, for every femtosecond, for every instant, for every click of the top of the clock. I will have a frequency. That frequency will change all over the map over time. It'll wander all over over time, but it will be, at any instant, it will be a single frequency. Very, very useful concept. It's called the instantaneous frequency. And again, from a point of view, from your point of view, from your point of view, if you have a very, very complicated theta of t, one thing you can learn about it is what is the frequency doing at any instant of time. And that's just a derivative away. Okay? I can use this, for example. Supposing I have an omega, and now this vertical, this axis that goes up here, I'm going to write as time. So I'll block off different lengths of time, or different instants of time. And maybe I'll start with my frequency over here. Maybe it'll jump down to here. Maybe it'll jump down to here. Maybe it'll jump back over to here. Maybe it'll have a very chaotic pattern as it travels through time. But I'll have a definite excursion and actually a way of plotting this signal. This looks to me a lot like a sheet of music, like sheet music, where I have time along the x-axis, and then the notes, the particular notes, inform me what frequency or what set of frequencies I play at any instant of time. Okay, and so we can get this from this kind of from this approach. Okay. Now, if you buy that, the derivative of phase gives me the instantaneous frequency, then you can say, well, the total phase that you accumulate over time, the total number of radians that this has gone through, in other words, the total angular extent, 2 pi, 4 pi, 6 pi, 17 pi, and so on, the total amount of phase angle that I have at any instant of time is the integral of that. So these two allow you to go back and forth between phase and instantaneous frequency. In general, we want to be writing expressions that look like this. And today what we want to do is we want to write them for frequency modulation and phase modulation. And so this will be complicated. And so what we'd really like to do is figure out how to write down this theta of t for whatever particular signals that we have. All right, so we'll start with phase modulation. The output of a phase modulator. The output of a phase modulator, what we send down our link, what we send out of our transmitter down the channel, will be that psi PM for phase modulation. And because A cosine will have a carrier, and usually when I write something like this, I'll always include a phase angle. I'll write it as theta. And this phase angle will now carry the message signal. So I'll write A cosine of omega ct plus m of t, the message signal, and I'll reserve the right to scale it a little bit by some constant k sub p. Okay? So here's my complicated expression for how the phase angle accumulates. And we know that M of t wanders all over the map. It can be a song that has so many different chords in it. It can be voice. It can be video. It'll go all over the map. So whatever M of t is doing, scaling by kp will contribute to the total phase angle that goes through this, that this cosine is taking the angle of. Okay. So this is my big old mess, and I want to try out what I just told you, which is the instantaneous frequency of a phase modulated signal will be the derivative of this. The derivative of the first term is omega c. The derivative of the second term, well, kp is a constant. And m of t is now a function of time. So take the derivative of that, and I get m dot of t. Okay. So this is my instantaneous frequency of a phase modulated signal. And this is how my phase gets accumulated. The question was, do I have to assign...
We just did the differentiation of... we just did the...
Oh, okay. I think I understand what you're saying. The question is, do I take d by dt of this signal, or do I take d by dt of this guy here to get the instantaneous frequency? And the answer is by this formula here, and it's a very good question. I'm really glad you... No, it's a great question, because if you're confused, other people are confused. So notice, let's go back to my definition or my prescription for how to calculate the instantaneous frequency. Here's a signal that varies as a function of time. It's a constant amplitude times cosine times theta of t. My instantaneous frequency is not taking the derivative of d theta of d phi dt. It's taking the derivative of what's inside the cosine. What's inside the cosine. And so that's d theta dt here. And so what I've done here is I've taken the derivative not of this expression, but just of what's inside of here. Okay? Excellent question. I'm glad you asked that. The answer is simple, but it reinforces the right definition. And I'm sorry I wasn't clear on that. Okay? So let's now do frequency modulation. And frequency modulation, let's think about what that means. That means the frequency of my signal is being modulated. The frequency of my total signal that I send down the transmission line, down the channel, is being modulated in accordance with the message signal. Okay? So the frequency of what I send down the channel, frequency of phi of t, is modulated with the information of m of t. So the way I'm going to think about this is I'm going to say my instantaneous frequency is a function of time for FM. My instantaneous frequency is a function of time for FM now has my message signal information in it. So it's going to be an omega c, and then it's going to have a term that has my message signal. And what I reserve the right to do is to scale that. I scale that message signal to get the right comparison, to get the right encoding on this. So I'll multiply that by a constant, and that constant I'll call kf, as opposed to k sub p, which I did for the phase modulation. So what I'm saying is for frequency modulation, not phase, but for frequency modulation, it's the instantaneous frequency that is modulated in accordance with m of t. And so I write down the form carrier frequency plus a component that's due to my message signal. Now what I want to do is I want to know for Fm of t, I want to know how to accumulate radians. I want to know how I accumulate radians. Well, this is my instantaneous frequency, and to get the accumulated radians, what do I do with the instantaneous frequency? I integrate it. So this theta of t is going to equal to the integral of the instantaneous frequency for Fm Oh, sorry. That's okay. You were probably right there. So let me try to use up the last little bit of this paper. So that's my form for my FM signal. So to summarize, I have the phase modulated form of what I want out of my phase modulator transmitter. For FM, I have that. That's odd. You should be able to see all of that from code. I have a slightly wide. Okay, that's wide. That's half page. And I need to, I guess I'll zoom out. My preset isn't quite right. There. That'll be a little better for you. Okay. And my instantaneous frequency for my phase modulated signal and for my FM signal It's that. So you'll see it's very close to the same form, except for one thing. The phase modulation is the derivative. The message signal in the instantaneous frequency is the derivative of the message signal, and here it's just the message signal. Whereas it's the message signal that's in the envelope of the cosine for the signal, and it's the integral of the message signal. So just to think a little bit about realization, I don't want to go into it too much now, but to think a little bit about realization, if I have an m of t, and I want to get to an m dot of t, what do I have to do to it? A high-pass filter will act like a differentiator. Okay. And similarly, if I have an m of t, and I want the integral of it, what should I do? Low-pass filter. Okay. So you see that if I have a message signal, I can decide if I want a phase modulation or I want a frequency modulation by what kind of filter I put in there. So the trick is, if I can realize one of these, I can probably realize the other one. If I can figure out how to realize one of these, then I can probably figure out how to realize the other one, because it's just a filtering operation, either low pass or high pass. So Kp m dot of t goes to that, or Kp m of t, there's a dot there, goes to Kf times the integral like that. Or, more generally, this waveform, this exponentially modulated waveform, has a more general form that's a times the cosine of omega ct, always a carrier in there, just to get me up into the away from baseband. That's the role of that carrier. And then we saw that we either put in the m of tau, m of t, or the low-pass filter of m of t. Now that low-pass filter is a convolution, of the signal with a low-pass filter response, but I can generalize that. To be that form. And here's something that should make sure you can read this limit of integration. That's a t. So this is a convolution. So now supposing h of t minus tau was equal to Kp times a delta function. If I put that in there, then the Kp goes through the integral. It's a constant. And I'm left with m of tau, del of tau, or del of t. The shifting property tells me that that integral is just m of t. In that case, I get phase modulation. Okay? So if I put Kp del of t in for h of t minus tau, then the Kp goes through the integral, and I'm left with the integral of minus infinity to t of m of tau dt, which is m evaluated at tau equals t, or m of t. Suppose h of t minus tau was equal to kf times the unit step function That unit step function is just a 1, so I'll pull out a kf times a 1. My limit of integration goes from 0 to t, but I won't worry too much about that. And if that's the case, then I have an integral of m of t, or m of tau d tau, accumulated up, and then that's my frequency modulation. Okay. So that gives you other ways of thinking about implementing or realizing this, and even other applications of where you can use this kind of a form. If anything funky is going on with your phase angle, if anything funky is going on in this phase angle because of dispersion in your line, multi-pass bounces from building to building in a wireless thing, you're going to have a funny phase oscillation. And so you'd encode or you'd model that phase modulation in a term that looks like this and try to glean out what's causing it. And then when you have your overall signal, then you can tackle how to get rid of it or how to mitigate it. Okay. So our general expression, the general expression for the exponentially modulated signal is a cosine of omega ct plus a mess, an interesting phase angle response. And the worst expression of that mess is that convolution. But I've also given you examples of what to do if it's phase modulated. Fairly easy, actually, there. It's just linearly with your message signal. Or if it's FM, then it's the integral. And in general, it's any convolution in between. So this is sort of the general expression. And that's what I want to work with to show you something. When I picked this form, or when we picked this form, with a constant amplitude in front of this, then we did a very nice thing falls out. The power of this signal is the average of this signal squared over all time. So I take this and I integrate. I guess this should be minus t over 2 to t over 2. Or I could do a 2t there. Square the signal. And I use my trig identity here so that it's 1/2 of 0 plus 1/2 of twice this, whatever mess is going on in there. I'm sorry, 1/2 of 1 plus 1/2 of whatever's going on in there. So that's a squared over 2. So just the trig identity giving you your DC term, and then your second harmonic. Whatever this guy goes, if I take a very, very, very long time, this guy is going to average out to 0. And so my power of my FM or my phase modulated or any exponentially modulated signal is going to be a squared over 2 and that's going to be completely independent of what goes on inside that envelope, inside the cosine. So what I've done is I've wrapped my message signal in the protective clutches of my cosine. I've paid a price of complexity and sophistication for that, but I've gotten some benefit out of it too. So let me sketch a couple of situations here. For the frequency modulated case, for example, and in fact what I'll do is I'll give a very specific example. I'll just do the simplest case because it's easiest to sketch, of frequency shift keying. And in frequency shift keying, what I'll do is I'll send one frequency until you're able to resolve that it's one frequency. Okay, a few cycles. You measure it, you detect it, and you see, yes, I made one frequency. And then what I'll do is I'll send another. Then I'll break and I'll send another signal. A couple of cycles there, and then I'll switch back and I'll send the high frequency for a period of time until you identify that. Okay. Now, if I block this off. And I'll be more careful about this now. I'll block this off into time slots. And I'll argue that I'll send a 1, a 0, and a 1. And so I'm beginning to send you a message encoded by the frequency of the signal that I send. And this is frequency shift keying. One example of a frequency shift keyed signal is if I had two light bulbs, two LEDs, say a red one and a green one, a red LED and a green LED. And if I transmit a red, I'm transmitting a 1. If I transmit a green, I transmit a 0. So I can go back and forth between red and green, red and green, red and green, and you can detect, visibly what my message signal is. And that's not a long leap from from that to a traffic light, with a red light saying stop and a green light saying go. That's a frequency shift keyed system. I'm ignoring the yellow, but you could easily imagine the yellow in there as well, a third frequency for a more complicated signal. But if I go back to what I was talking about with the power. Go back to talking about the power. The average power that I transmit here is all the same. Because on this side it's just a squared over 2, a squared over 2, a squared over 2, a squared over 2. So the amount of power that I send at any instant of time has not changed, because the message is inside the envelope of the cosine. And let me remind you of what an amplitude modulated signal looks like. An amplitude modulated signal, to send something sort of similar to this, would mean that I send out a lot of power here, no power, and then a lot of power there. And so the average power of my AM waveform, or my instantaneous power of my AM waveform, is changing all over the map. One of the things that we'll do in a little bit, not today, but in a little bit, we'll look at it. We'll look at such a channel, and we'll say, okay, supposing a channel is nonlinear, and in a nonlinear channel, the amount of the signal, the response of that channel depends on the amount of signal that I send through. So the response of the channel is one thing up here and another thing here. And so the distortion, there's going to be distortion from a nonlinear channel on an AM signal that won't exist on an FM signal. The channel will behave differently here, here, and here, which means the distortion will be different here, here, and here, versus for the FM case, constant amplitude, constant material, constant channel. No such complexity. So there's some trade-offs. There's some trade-offs of when to use one versus the other. Now, one of the big questions that we have to ask ourselves, for FM and for PM is what kind of filters we use in our system. Or another way to put it, what is my bandpass? What is my channel? What is my allocation? What is my frequency allocation for an FM radio station versus an AM radio station? In other words, if I implement an FM signal, how much bandwidth am I using? It's one of the most fundamental questions, because all your bandpass filterings, whether or not your channel can support that, we need to know where that energy is, not in time, but rather in frequency. Where is it spread in time, in frequency rather than time? So what's the bandwidth of exponentially modulated signals? And I'll start with FM. I'll probably end with FM too. It's not terribly different. The construction is not terribly different in either case. And I'll break down what I know about FM. And that's my instantaneous frequency. Now, one way to approach this is to go to my, what's that, a sonogram? Frequency as a function of time. And to watch my signal for a little while. So I'm centered around some omega C here. And my frequency is going to wander. My instantaneous frequency is going to wander. And it won't be perfect, and it won't be the best way of doing this. But what I can do is I can sort of draw some lines, and I can say, there's my frequency spread. There's my bandwidth of my FM signal. Just observe it for a while. Okay? And ultimately we'll do that. Ultimately we'll carefully go through and carefully do some theory to do that. But before I do, we want to appreciate just how hard this problem is. Okay? And so what I'll do is I'll say that our phase angle will be the integral of the instantaneous frequency And then what Lati does is he doesn't like writing that integral, so he calls this A of t. It's just to save some notation, just to save some space. Not really that big a deal. And then he writes in complex notation. That's what that hat means. E to the j omega ct kf a of t, where this guy here is theta of t. I think we're along about equation 5.7 or 5.6, 5.6, 5.7 in Lati, just to give you a reference of where we are. And so I'll separate this out. And this stuff is pretty easy. This stuff in here I'll write as a Taylor series. And then I can't forget about that guy, e to the j omega ct. And to recover the actual non-phasor notation, I take the real part of this. And the real part is influenced by cosine plus j, cosine of omega ct plus j sine of omega ct. And then all these j's, whenever my n is odd, I'll have a leftover j. And so that j will multiply by the sine term, the j sine term. And that'll be my real part. So Okay. So this now almost looks like an AM signal or a summation of AM signals. This looks like a summation of AM signals. One at cosine and one at its quadrature, another one at its cosine, another one of its quadratures. And that's not bad. But there's a problem. And look at what's happening to this A of t. And that A of t is the message signal. It's the integral of the message signal, but I won't split hairs with you on that. So I have an A of t, I have an A squared of t, and I have an A cubed of t. And the last I checked, this message signal was a random signal with a whole bunch of different frequencies in it. And so if I had to implement that or model that message signal, what I would do is one thing I could do is I could write a Fourier series for it. And if I wrote a Fourier series, I'd have a bunch of cosines and sines there for my message signal. And all those cosines and sines would be to the first power, the second power, the third power, the fourth power, the fifth power, and on off to infinity. Okay? Well, let's just take a look at one of those terms of the Taylor series. Or rather, the Fourier series for A of t, the integral of m of t. Okay? So A of t, or rather, and that's what would go here. A squared of t will be cosine squared of omega 1t. And that would give me twice the frequency bandwidth. So if I start with that single frequency of omega 1 in my message signal, automatically I've got 1 at twice omega t. 1 at twice omega 1. That's only for my first term in my Taylor series. For A cubed of t, I'm going to have terms that are like cosine cubed of omega 1t. And that's going to give rise to terms of cosine of 3 omega t. So a to the n will give rise to cosine of n omega t terms through all the trig identities. And what that implies is a diverging bandwidth of this signal. What it implies is a diverging bandwidth of the signal. Yes, sir.
Does that mean for every instantaneous frequency there's harmonically related components in the actual signal?
No, that's a really good question. So the question is, where is my little map? Here. What you're asking is, do I have a comb of frequencies that's wandering around? And the answer is that's not my interpretation. My interpretation is that there is one frequency. There is one instantaneous frequency, not a comb of frequencies. But the signal itself is described as a okay. The difference is what's going on inside of the cosine versus what's going on with the overall signal that I send down the line. Okay? And it's this. So this could be very, very well behaved, but this guy here, what I send down the line, that has a bandwidth. And that's the bandwidth that I'm interested in, because that's the bandwidth that I'm going to have filters on. That's the bandwidth that the FCC is going to charge me money for rent to use it or to sell it. So that's the issue. Now, the first thing a theoretician does is to truncate the series. Now I can do that. So if the AFT is well behaved, of a certain magnitude, and KF is small, then maybe I can get away with this to truncate my series. And this is called, and it's an oxymoron, narrowband FM. Because there is nothing narrowband about FM, but this is just in the literature called narrowband FM. And it comes about from truncating that series. And at first glance, it's a silly mathematical thing to do, because it's not representative of the KFs that we want, and it's not representative of all those terms that are generating the interesting behavior that makes an FM signal an FM signal. So you're very tempted to overlook this little theoretician's device until you decide that it's ridiculous. This one is ridiculously simple to realize. Okay? So if I wanted to realize this, I would start with I would start with AFT. I would start with a local oscillator. Remember, I'm trying to realize this with what I have in my kit, what I have in my toolbox, what I have in my fishing tackle box with all my components. And I know I have local oscillators around. I have used phase shifters before, so I can turn this cosine into a sine. And I can modulate or mix AFT with this sine. And I might as well amplify it by some amount KF. And now this guy here, on this arm here, I have KF AFT sine of omega CT. Right? Start with a cosine, phase shift it, mix it. And if I do the phase shifting right, I can even get a minus sign in there if I want to. Right? And then I also, on this branch here, I've got a cosine. Actually, I even multiply that by a capital A, right? Because I started with a certain strength of my oscillator. And here I have a cosine of omega CT. So all I have to do is sum these together. And then I have psi narrowband FM as a function of time. So from a realization perspective, I can realize this. And this is narrowband FM. Question for you. How would I realize narrowband PM, or phase modulation? What kind of a filter and where?
Bandpass around the carrier?
No? The answer was a bandpass around a carrier. So that would be limiting here. But my carrier doesn't need a bandpass because it's a single frequency. I hope I've paid some money for that. And I know what omega C is. I'd like to think that. So what do I have? Where is my message signal?
Would it be a low pass before you get to that, or the AFT?
Right. Okay. So remember, the question is for phase modulation. So A of t is equal to the integral of m of t dt. And what I'd like to do so A of t is coming in here. That's the integral of m of t. So let's hunt down our little list that lets us go between. We want inside of that to be m dot of t. So what we'll do is we'll use a filter A of t to get it to a PM. Okay? Now, it turns out that there's a brilliant way of implementing what's called wideband FM if I have narrowband FM. So if I have a message signal, and I prepare this so that it's either M of t or m dot of t, depending on whether I want to do FM or phase modulation, and I go through this realization to give me narrowband. If I want to go from here to all these other harmonics, what I do is I generate them. So I'll go through a highly nonlinear element a frequency multiplier, a highly nonlinear element, and that will give me my wideband FM. And it's not exactly FM, but it's pretty good. It certainly has a form that's close enough that we can call it FM. Remember, we have an idealized theory. When we go to realize that even at the system level, we may not get it perfectly. Step functions and delta functions step in, and those singularities make it hard to perfectly realize. In this case, I'm limited with my building blocks, and so I have to. So, what would I use for that frequency multiplier? A highly nonlinear element, a diode or a transistor. A resistor would be just a straight line between the IV curve. But as long as that IV curve curved, then I'd have then different frequencies would see different transfer functions, and so a diode would be a brilliant idea. So yes, a diode acting like a frequency multiplier would take the frequencies here that are generated and smear them out and spread them out into a wideband FM. And this is called the Armstrong method to generate frequency modulation. And I have just 5 minutes I have left, and so I will tell you a half-hour story in 5 minutes on who Armstrong was, and in my estimation, he was one of the very best electrical engineers that's ever been, Edwin Armstrong. And he grew up in the early part of the 20th century, so 1900s, 1910s, 20s, and so on. And there was this great invention that hobbyists were able to access called wireless. Marconi demonstrated wireless from ship to ship or ship to shore, eventually crossing the Atlantic in just an incredible feat. And the components to build wireless were accessible to any hobbyist. And Armstrong grew up a little bit, up the Hudson from New York City in a very nice house. His parents had money, and he was able to put together diodes, vacuum tubes, and things of that nature. He came up with 3 incredible inventions. One of them was the concept of negative feedback on an amplifier. And it's not obvious at the time because your amplifiers were horrible. An op-amp with a gain of 10 to the 6th is one thing. An amplifier with a gain of 1.5 was a remarkable thing. So how do you use that? Well, the last thing you want to do is bring your signal in and out of phase, so you cancel it. So he thought up the idea of negative feedback, which is a concept which is something we use every day to build an active filter out of an op-amp. That was his first great invention. If I had more time, I would tell you the story of how he lost that patent. But that's another interesting twist. He also came up with super heterodyne as a detection and technique, and that's found in every single FM radio today. And that came out of his work during World War I. Well, it's a mixing. It's actually that. It's a mixing. There's some other tricks to it, but it's basically the mixing of a local oscillator with a signal. So the super heterodyne mixing was a way of doing that. It was very economical and really changed the receiving, particularly of these radio sets. The last one he did was this FM, and RCA, the Radio Corporation of America, rolled out the whole wireless industry, the whole radio broadcasting industry. And at first, Armstrong was very tied up with David Sarnoff at RCA, but they split over this business of FM versus AM. By the time Armstrong came up with FM, the AM infrastructure was widely in place, and it would have been prohibitively expensive for Sarnoff to roll out a whole new set of transmitters, receivers, radio stations that were now on FM. Sarnoff was an excellent businessman and, in fact, a ruthless businessman. And one of the techniques that he would do would be to hire from the FCC.